Hi, class. I want to start on muscle metabolism, but I thought about something I didn't include in my last video on isometric and isotonic contractions. And I thought about it, and I want to bring that up. Then we'll go immediately into muscle metabolism. Okay. Remember in the last video, we were talking about isometric contractions. And we were saying, and isotonic, and we were saying that under the isometric contractions, isotonic, we had the concentric, and I was saying the barbell thing. Okay. Here would be you're lifting a barbell, and that's a concentric, the muscle is shortening. Here's eccentric, you still have tension, but you're letting it out. You're letting it out. Same thing here. So I just wanted to show you what I was saying. The other thing, though, I want to bring up real quickly is this. If you were to stretch your arm out totally and try to lift a weight, to have it totally stretched out, and you wouldn't be able to generate the same tension. Now, let's say that you had it in way like this here, way up. You can't generate the maximum tension. So whether it be this way or this way, even this way or this way, see how the muscle is so stretched out? You can't, so the best tension is not in this position or that position. It's really in a midway position. Now let me show you why. Okay. Why it's hard to lift when the muscle is stretched too much or it's in too much. It has to do quickly with this curve here. Remember we said these were sarcomeres. Okay. If you're in so far short, then see the heads right here. Let's see if I can do something here. The heads right here cannot touch that part of actin. So you can't have maximum myosin touching actin because it's too short. So that overlap part right here the myosin can't grab it to get a better hold. Here is out too far. Only the tips can get it. That's when your arm is stretched out too far. So the optimal sarcomere length, this is what we call optimal sarcomere length, is up in here. Ergonomics uses that to show you how to lift and your chairs and everything like that. So this becomes, because see, every feather head of the myosin can touch actin. Here, you can't do that. Here is too far out. So that's the reason there's a certain length you can put your muscles at and have a stronger lift. Okay, I wanted to bring that up. Okay, now we're going to another subject. And that subject is metabolism. Okay, so that's where we're going now, muscle metabolism. So let me go down here. All right. Now, what we have here, let me make this a little smaller. So you're getting ready to, this is where it comes in. You're getting ready to do a contraction or do an exercise or do some running. Okay. Now, ATP, as we said, is your energy source. ATP is your energy source. So the question comes as to how do you get the ATP? The question comes as to how you get the ATP. All right. In your muscle cytoplasm, you have enough ATP to get you kicked off for about 4 to 6 seconds. So when you first start using the muscle, about 4 to 6 seconds is stored ATP. Now, why can't you store more? Because ATP likes to discharge too quick. It is an energy battery for us, but it discharges quick. It doesn't hold that phosphate. Phosphate wants to get away. So only about 4 to 6 seconds can it have. The other extra would just start discharging without anything. And of course, we said if you release energy and there's nothing to harness, it goes away as heat. All right. The next thing we have, I'm sure you heard of people taking creatine, is creatine phosphate. Okay. That's about 15 seconds. We'll look at in just a moment. Then glycolysis we'll look at will give you about 45 seconds, sometimes up to a minute. But if you're going to do the long running, the marathon, you got to break into the Krebs cycle. Now, you're going to need oxygen to do that. See, all these others, you didn't need oxygen. But this one, to get endurance, you're going to need oxygen. So let's just look at that briefly. Okay. So, person's running. The most immediate source, which you don't see here, is going to be ready ATP when they first take off. Now, if they're running, let's think about it. Let's go back. If they're running and they're doing the 100-meter dash, they pretty much only need this and a little bit of that. The fast people may not need no more than this. Okay. But if you are running longer distances, you're going to need more. All right. So the short-term lactic acid and so forth, we'll see what we're talking about. All right. Energy for muscle contraction. Initial muscles use stored ATP. Okay. That's what we said earlier. Then with the creatine, this is what you do. Creatine phosphate re-energizes ATP. So it's like a portable battery charger. So what would happen is the ATP that you discharge, that 4 to 6 seconds, you have some creatine phosphate in you. Some creatine phosphate. You can make it or it can come in through the diet. The creatine phosphate then will give up its phosphate because it has a higher energy than ADP. So the creatine phosphate will give its phosphate to restore your ADP to ATP. So in other words, it's acting as a backup to help restore those 4 to 6 seconds. Now, in the average muscle, let's say, you have about 15, let's say about right here, about 15 seconds. Now, some people take that creatine and make creatine phosphate. You know, that's one of the things that's taboo in competitive sports because you're given an unfair advantage. You're given an unfair advantage. There was one guy, Mark McGuire, that had hit a bunch of home runs. He was just firing them off, and then they found later that he was taking creatine. Okay? Now, here's the other problem with creatine. Taking a lot of creatine, the only spot when we get an ANP2 that creatine is eliminated is in the kidney. Let me say it again. The only spot it's eliminated is in the kidney. So when you're taking too much, it can start causing kidney damage. It will give you energy, but it can cause kidney damage. All right, let's go to the next one. Glycolysis. Glycolysis doesn't need oxygen. You're taking glucose. Now you're starting with glycogen. Remember, glycogen is a storage form of glucose in us. And glycogen is made up of a bunch of glucose. It's covalently bonded. So in a muscle cell, you're starting to break down your glycogen. You split off a glucose, and the glucose would go through several steps of reaction, about 10 steps, and you would end with pyruvate. Now, I'm going to put something in here real quick. So, you do 10 steps of enzymatic conversion. 10 steps of enzymatic conversion to get a net 2 ATPs. All right, let's think about that now. What is net in math? Add, subtract, divide, or multiply. What's net income? Gross income minus taxes. So net is you have to subtract. Net you have to subtract. So you actually make 4 ATPs. Make 4 ATPs in glycolysis, but use 2 to make them. So therefore, you're only getting a net of 2. You're doing 10 steps to get a net of 2. But what's the advantage? You don't need oxygen and it's quick. You don't need oxygen and it's quick. All right. Now, pyruvate, let's say, is the final thing. But pyruvate can be converted into something called acetyl-CoA if oxygen is around. If oxygen is around, pyruvate can be converted to acetyl-CoA. When that occurs, but again, oxygen has to be around, that can enter inside the mitochondria. Remember the mitochondria? We kind of talked about this before when we did the cell. That can enter into the mitochondria and you can do the Krebs. Now here's the difference. The Krebs cycle, I'll come here. Let's do our thing. The Krebs cycle, 8 steps, but 32 ATPs. 8 steps, but 32 ATPs. So if you can get the oxygen going, you can get a lot more with fewer steps. So that's why when we go back here and you look at what I have, once you break into that, that's where you can go for hours. Once you break into this Krebs cycle, and then see from the Krebs cycle, we discussed it, you get electrons, and the electrons go through the electron transport chain, which is another area of the mitochondria. So all of this works together. All of this works together to give you that long energy. But what do you need? Oxygen. But what do you need? Oxygen. So see, that's what this is showing, and you can kind of study it. Now here's right here, let me show you something. If you go through the glycolysis and you don't have oxygen available around the muscle cell, then pyruvic acid will convert to lactic acid. It won't go to that acetyl-CoA, and the lactic acid will start to burn the muscle. That's the burn in the muscle. But ultimately, so that you don't denature the protein, see, no oxygen, it's released into the blood. Okay? So that's the point I'm saying. And then as far as energy, you see, you can even burn fatty acids. They all can go in through the Krebs cycle. They all can. But the key is that 32. The key is if you can get that oxygen, there it is, then you're really going to get that endurance. That's why that oxygen is very important. So in your book, you can look at this here. You can do that on your own, and you can see what I'm talking about there. All right. Now here is just a little discussion on that creatine phosphate. And we can make it in our body. We make it from 3 different amino acids put together to make the creatine. Okay, but we also can take it in the diet. Okay. Now, the other thing to speak on real quick is muscle fatigue. What is muscle fatigue? That means you're running out of ATP. Now let's think about it. You're running out of ATP. Okay, so you're going to start to have potassium and calcium problems. Why? Because if you run out of ATP, it's kind of like rigor mortis in a way, but not to that extent, don't get me wrong. You can't bring the potassium back in. You can't bring the calcium back into the sarcoplasmic reticulum. So you start having interfere with that EC coupling. Prolonged X damages the SR and interferes with calcium regulation, as I mentioned. Now, total lack of ATP, you really never go to that in the cell hardly. That's real rare. Okay. But in the muscle, I'm going to come to one other thing. Let me see if I missed it. The oxygen debt. We call it an oxygen debt. Okay, this is basically what this means is that you still need to reduce some more oxygen after you stop exercising. That's why you're panting after you exercise. So read on this oxygen deficit. That's why you pant after an exercise. Muscles are about 40% efficient. Most of the energy goes as heat, but we're homeotherms. I'll close here.